Okay. I've gotten a few questions today about latest homework on vectors. So I'm going to choose one of these problems. And oops, okay. All right, and I'm going to take a look at the last problem, number 14. Okay, so I'll discuss it using the numbers that I'm getting in my version of a question. So do this equation, x squared plus 6x plus y squared plus 5y plus z squared plus 4z 0. This is square of the sphere. What we said was 7 bases. I actually did cover an example of this, but I suppose more is always better. Okay, but this so everybody's aware that this stuff is in the notes. Now, what we do by grouping x, y terms together, on each one we're going to complete the square, because to have the equation in a form where you can easily see what the center and radius are, we want it in this form: x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. So then r would be the radius, and then the center would be x naught y naught z naught. So what do you need? What you need to do in this problem is get the equation from this form into this form by completing the square. And for that, use this formula that I gave when it's first covered. Okay. Then you have x squared plus bx plus c. Notice I have no coefficient in front of the x squared. So if you're in this problem, the coefficient of x squared, y squared, z squared are all 1, so there's no problem. But if there was coefficient in front of those, and for a sphere, it all had to be the same coefficient, then you should divide by that before you continue. So the formula used for completing the square is the following. If I have x plus, let's make something up here, alpha squared, then what we get is x squared plus 2 alpha x plus alpha squared. So whatever the coefficient of x you have here is always twice what's being added to x when you in the square completed form. Well, here we have bx, which corresponds to the 2 alpha down here. So whatever you have in front of the x, half of that is always what goes here. So you have x plus b over 2 squared. Okay. And the c just comes along for the ride. But what you can see from squaring this out is you also get the term of alpha squared. So if I were to square this, I'd get x squared, which I want. I'd get bx, which I want. But then I get this additional term that I don't want. This squared, b over 2, the whole thing squared. So now I had to subtract that off to compensate. Okay, so that's the completing the square formula for this case. So you need to apply this to each group of terms in parentheses. So corresponding to first for x, and then for y, so you have y here, and then again for z. So in the case of x, you have x squared plus 6x. So b is equal to 6, and there is no constant term here. So c would be equal to 0. So you use that down here, and you get x plus 3 quantity squared. And then what? Not yet. We're not done with x yet. All right, so from this, I get this, but look down here, I get something else. Yeah, minus 6 squared over 4, which is 9. So now we're done with x. All right. Then you move on to y. So what would I get from y?
Five over 2.
Yes, so y plus 5 halves squared. And then whatever term needs to be included.
Minus 25/4.
Yes, so the number's not working out very nicely. Actually, I'm going to look at the. Oh, yeah, the numbers definitely don't work out nicely. Okay, all right, that's y. And then finally, for z.
Minus 4.
Yeah, wait,
4 squared over 4 is 4.
yeah. Sorry, I put a different number in my head. Okay. Yeah, so b is 4, so 16 over 4. All right, and all that still equals 0. So we can see what the center is now. So the center is, what is the center? Keep in mind, relating this form to now, this form is the one that reveals the center and radius. Yeah. All right, now that's the center. Now for radius, we need to take all these constants and move them to the other side. So we have, so if I rewrite this, so x plus 3 squared plus y plus 5 halves squared plus z plus 2 squared equals, so then we get all the constant to move them to the other side. So we have 13 plus 25 over 4, which is 77 over 4. And then what do we do with that?
And r is the square root of 77.
Yeah, because that number that it's got there.
Let's say square root of 77.
Yeah. So that means that r is, so because this is r squared from our form over here. So r is square root of 4, which could also be written this way, it doesn't matter.
If you want to get technical and fancy.
Yeah. Okay, and so that's roughly 4.339. I want to go to 2 decimal places. Okay. Any questions about how this played out? Or any other one from this homework? Okay. So as we go, I'm putting out new homework assignments. So looking ahead to the end of the semester, we're going to have 13 homeworks in total.
You know, we've got a lot of stuff coming over the next month.
Yeah, unfortunately, well, unfortunately, yes. Well, yeah, we have, including today, we have 5 weeks left of classes. It's a little bit past the 2/3 mark. Right. Okay. So. We're working in three dimensions. So here's a portion of a plane in 3D. And if I have two vectors that are meant to be contained within this plane. So we're trapped inside it. So I'll call this one U and this one B. Now. The two vectors U and V that both belong to vector space R3. They've also written as D3 in the past. Are contained within a plane. Then any linear combination of U and V, and by that I mean multiplying U and V by scalars C and D and adding them up, would also be in the plane. So I could think of this plane as being defined by all possible linear combinations of the vectors U and V. Now, suppose I draw in here a vector I'll call W. I'll have to move this U over here. Just to reduce clutter. Now suppose the vector W is perpendicular or orthogonal to both U and V. So another way of putting it, if, the dot product of W and U is 0, dot product of W and V is also 0. So if W is orthogonal to both U and V, then by the properties, I think this is y'all working now, just supposed to wait. The better properties of a dot product covered last time, this dot product, so this is D right here, is equal to C times the dot product of W and U plus D times the dot product of W and V. But both of these are 0, so the whole thing is also 0. So W is orthogonal to all possible vectors that sit within that plane. So what we can do is we can define this plane as instead of all vectors that are orthogonal to this vector W. Okay. So, but also passing through a particular point, which we're not going to deal with today. So, the reason why I'm telling you this is, if a vector W is known, then that makes it easy to come up with an equation of a plane. So it'd be nice to have some way of coming up with it. Because the general equation of a plane is something this form, ax plus by plus cz plus d is equal to 0, where x, y, and z are the coordinates at any point in the plane. And then a, b, and c, a, b, c, d are certain numbers, very constants. Okay. All right. So we'd like to have a way to come up with these constants, and knowing what vector is orthogonal to the whole plane will help us get that. Because so it turns out what we'll see later is that the vector W we're looking for gives us numbers A, B, and C. So with this setting in mind, the problem we're going to look at today is if we're given two three-dimensional vectors U and V, how do we get a vector W that is perpendicular to both U and V? So that's the part of this we'll focus on today. And then later we'll come back to planes and learn all about how we get this equation. So now this is a actually more generic problem that has uses beyond planes. That's the application that's of interest to us in this class. Okay. Now, to find W, we can use these equations right here. That's dot product of this unknown vector W if U is 0 and dot product with V is 0. So what I can do is I can express U, V, W in there as their components, in terms of their components, and then I'll write out what these two equations mean. I can let U be the vector 1, 2, 3, and then similar descriptions for V and W. X, Y, and Z components. And now I bring back these two equations. U dot W must equal 0. V dot W must equal 0. So the first one, I was right using a definition of dot product. We multiply corresponding components and add them up. And this must be 0. Same thing for V dot W. zero. Now, I won't go through all the algebra right here, but you can find it in the notes. We wanted to. We have three unknowns, W1, W2, W3. But we only have two equations. Can anyone tell me, what does it mean when we have fewer equations than unknowns? In terms of how many solutions we might have. There's a free variable. Yeah, so you would actually have infinitely many solutions. Especially when it's a homogeneous system, we know for sure that we have infinitely many solutions. Now, I'm going to write down a solution that does not require us to perform any divisions, because we don't have to make any assumptions about these components of U and B having to be non-zero. So if we can avoid dividing by any of those, then that would be helpful. So with infinitely many solutions, but solution of interest to us is this one, the vector that has let me try this. Let's get write it down first, and I'll explain where it comes from. 2v3 minus u3v2. So this is the x component. Then I have u3v1 minus u1v3. And then the third component, the z component, is u1v2 minus u2v1.
This is the matrix multiplication.
Actually, it can be written in terms of a determinant. Yeah. And I'm going to label this as u cross v. So we have an x in the middle of a multiplication x. And this is called the cross product of u and v. Okay, so that's the definition. Okay. Now, a commonly used way of working this out is it is the determinant of this matrix, where I put the vectors I, J, K, the standard basis vectors, fill the top row. And then the first vector in your cross product fills the second row. And then the other vector in the cross product fills the third row. So if you know how to compute 3x3 determinants, that would give you the correct vector.
Yeah, so it's like you cover up the
Yeah.
first row and then do like U2 times the U3 and then.
Yes.
U3 times
Like if you're
U2,
trying to
and then
find,
second row and then third row.
I
Yeah.
thought it was called matrix, not determinant. That's my.
Well, okay, yeah, determinant of a matrix. So,
Yeah,
So-
sorry, I just had to remind myself of physics 1.
yep, so we look at the ith component. That involves the 2x2 determinant of this matrix, and that's how that expression came about. So u2v3 minus u3v2, so these two minus the product of the other two. So that, and because it's multiplied by the vector I, that it gives you the x component. And then for J, rules of computing 3x3 determinants, you would actually go minus J times determinant that you get by covering up this first row and the second column. So then you'd have u1v3 minus u3v1. So this times this minus this times this. I realize it's getting cluttered. But then you have a minus out here, which is why this expression right here is the negative of this one. Okay. And then you go plus K. And then you cover up a first row and the third column, and you work with 2 and 2 determinants of that matrix. U1, V2 minus U2, V1. That gives you the X, Y, and Z components of cross product. Okay. Now, we've just seen between this class and last class, 2 operations that can be performed in vectors that both are called products. Students get these 2 confused all the time. So, it's like a little chart, but comparing them, contrasting them. So the dot product of 2 vectors u and v, indicated by the dot in the middle, that is a number. Whereas u multiplication x, v cross product, result of that is a vector. So we're very different animals here. Dot product is defined in any number of dimensions. And in this class, we're only concerned about vectors in 2-dimensional, 3-dimensional space, but you can have vectors in any dimensional space, and we know what the dot product is. No matter how many dimensions there are, you're multiplying corresponding components, and then you're adding them all up. That's so for cross product. Cross product, as I've given here, only makes sense in 3 dimensions, because that's the only number of dimensions in which there's a unique direction that is orthogonal to 2 other given directions. There are analogs to cross products in other dimensions. For example, if I have 3 vectors in 4-dimensional space, then I could do something like this, sort of a 4x4 matrix to find a vector that is orthogonal to all 3 of them. Last time I showed you, given 1 vector in 2 dimensions, how you get a vector that is orthogonal to it. But as far as a binary operation like this, where you're operating on 2 vectors and get a vector that's orthogonal to them both, this is only for 3D. In higher dimensions, if you only have 2 vectors and you want something that's orthogonal to both, there's not a unique direction for that. There'd be infinitely many directions. Both products have formulas, relevant formulas that involve trig functions. For dot product, we saw that dot product of u and v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. We have something similar for the magnitude of the cross product. So remember, a cross product is a vector. The magnitude of that vector is equal to magnitude of u times the magnitude of v times the sine of the angle between them. Keep in mind that the angle must be between 0 and pi radians, or 0 to 180 degrees, just so sine is non-negative, because certainly the magnitude of a vector has to be non-negative. This formula is derived in the notes. You can see all the ugly alphabet there. Questions so far, especially about the contrast between them. There'll certainly be questions in the final, given these vectors compute a dot product or cross product. And this is the same class that mixed up techniques for working with sequences with techniques for working with series. So I'm hoping that that same kind of mix up won't happen again.
I have a question.
Yep.
Will there be notes on the final similar as to there was on the first exam? Like a cheat sheet of sorts?
Okay, let me see what I've done in the past fair. I've not yet started composing the final. Oh, I have. Okay. Look, I pulled up one of my exam files and there wasn't one there, but yes. Yes, so and I'll certainly recycle that for this. So some things that would be on the cheat sheet, the formulas for dot product and cross product, magnitude of cross product, formulas for going between Cartesian and polar coordinates. And there'll be some other ones that I haven't covered yet, but yes, you will get a cheat sheet.
Okay, perfect. Thank you.
Okay.
Never a question? Okay. Now, as far as so the properties of the cross product. So what is the cross product to be orthogonal to both U and V? As I mentioned before, that would be any solution of this system, but infinitely many possibilities. Now, if I also specify that the magnitude of this vector W has to be equal to this, magnitude of U times magnitude of V times sine theta, that narrows it down. So there are only two vectors possible that are orthogonal to both U and V and have this magnitude. But it's still not unique because I could have a vector pointing in this direction that would satisfy that, and also pointing in the opposite direction. That would still be both would still be orthogonal to U and V. They both would have this magnitude. So there has to be a way to make that unique. One way that's taught in the physics class is does anyone know what I'm referring to? Who's taking a physics class?
Can you repeat the question?
Since there's two possible vectors that are orthogonal to both U and V and have this magnitude, how do we determine which one is the correct one? What? Oh, no, but that's already accounted for. It's a right-hand rule. What the right-hand rule is if you have point your fingers in the direction of one of the vectors, like vector U, and then that has to be the first vector in the cross product, and then you curl your fingers in the direction of the other vector V, then it's whatever direction your thumb is pointing in.
It's like a third thing like this.
Yeah, and there was a time when I was taking a physics class, in the middle of a test of doing a right hand rule, only discovered I was doing it with my left hand. Yeah, so thankfully I caught that.
This is why they call it the right hand.
My right hand was busy writing.
That makes sense, like, you're writing that stuff down, you absentmindly are like doing it with your left hand.
Yeah. But I was already kind of stressed out because I had shown up to the test and then realized that I forgot my calculator. And I had to literally run back to my dorm and get it. So, yeah, that test did not go well. So, okay. Of course, just using this formula, that does it for you. That gives you the vector that's orthogonal to both U and V, has its magnitude, and honors the right hand rule. Okay. I think I have some examples back here. Yes. Okay. All right, so let's suppose that U is equal to vector 2 minus 1, 1. B is a vector 1, 2, 1. And we find W to be the cross product of U and V. And what I like to do if I'm carrying out a cross product by hand like this is I write the first vector on top, I write it vertically. So first vector on top of the second one. Then I see what I'm doing for my two by two determinants. So for the first component of a cross product, we're working with the second and third components of U and V. So I can work with these four right here. So I have -1 times 1 minus 1 times 2 for the X component. For the second component, the Y component, I'm using the first and third elements of U and V. But start from the upper right. Whereas before I started from the upper left. So I have 1 times 1 minus 2 times 1. And finally, for the third component, the Z component, I'm working with the first two components of U and V. So I have 2 times 2 minus -1 times 1. So then we go ahead and work all that out. Get -3 for the X component to -1 for the second component, and then 4 plus 1, so 5 for the third component. And time permitting, it's a good idea to check that this vector really is orthogonal to both U and V. So U dot W, so I'd have 2 times -3 plus -1 minus -1 plus 1 times 5. So I get -6 plus 1 plus 5 is equal to 0. So that's a good sign that you got it right. And then you can do the same for V and W. So we have 1 times -3 plus 2 times -1 plus 1 times 5. And that turns out to be 0 also. Okay. Questions about how the cross product was computed in this case? For a sense of cross product can be seen as computing a terms of a 3x3 matrix. There actually is a nice little trick that's specific to 3x3 matrices for computing determinants. It might be a little easier to remember. I can write out what that rule is, and I always forget what the name is.
Maybe someone knows what I'm referring to, but I'm going to look it up. Okay. Love all the Google results don't say what the name of it is. Dang it. Ah, the rule of Saros.
That was something on Star Trek. I'll write it out for a general matrix. The entry, 3x3 of entries A, B, C, and this only works in the 3x3 case, unfortunately.
The two first columns
Yes,
to the right.
yeah. So what you do is you write out the matrix, and then you write out you repeat the first two columns. Okay, and then you draw these diagonals, these three, and then you draw three diagonals going the other way. So what happens is the diagonals going from upper left to lower right, you multiply all the numbers on those diagonals. So A, E, I plus B, F, G plus C, D, H. And you add those. Then you take diagonals going from upper right to lower left, multiply all the numbers in those diagonals, and you subtract those. So minus C, E, G minus A, F, H minus B, D, I. Yeah.
So it's regarding this.
Yeah.
Okay? So, to calculate the determinants, so first you did for the last two columns,
Yeah.
minus 1 times 1 and then this.
Yeah.
And then we come to the second one.
Yeah.
2 times, why is the 2 times 1 on the second side?
Oh, because of what I showed you earlier when I was doing this as a determinant. Okay, so I take this element times the two by two determinant minus this times 2 by 2 determinant. Because that's side minus there, that's why it's going the other way. Yeah, so it comes from what's called a cofactor expansion of 3 by 3 determinant. That's why it's the only one that has that reversal. Right. Okay. Other questions? Okay. All right, so here's some properties of the cross product. Okay. First, so the cross product, unlike the dot product, is not commutative. It is anti-commutative. Meaning that if I take a cross product of V and V cross U, that is minus cross product of U and V. So changing the order of the vectors involved flips the sign. So be careful about what's being asked for, U cross V or V cross U. And from a formula that I would have written earlier, you can see if you reverse the roles of U and V, it just changes the sign of everything. If you scale one of the vectors involved in a cross product, that works out nicely. It just scales across product. So if I have the constant times U cross V, I can compute the cross product of U and V first, and then scale that by C. There is a distributive law with respect to vector addition. So if I have two vectors U and V, I add them and then take the cross product of W. That's the same as taking a cross product of W with U and V individually and then adding them. So at least that one works out nicely too. There's also a law that relates cross product and dot product that'll come in handy later. If I take U cross V and then take a dot product of W, that's the same as if I took the cross product of W and U and then took a dot product with V. Notice that the way in which the vectors are written is the same in each case. That's important. This is called a triple product of vectors U, V, and W. And finally, if you have three vectors involved in a cross product, so you do U cross V, that's a vector. So when you take a cross product of that with W, that's actually be expressed in terms of dot products. So we have W dot V times U minus W dot U times V. That's okay. And one other particularly notable property is if the vectors U and V are parallel, meaning V is equal to a scalar C times U, then their cross product is the zero vector. And that comes from properties of determinants. In a matrix, if one row is a scalar multiple of the number row, the determinant of that matrix is going to be zero. Now, the whole discussion of cross product started with being able to write down equations of planes. But there are a couple other geometric uses of a cross product. One is for area. Now, suppose I have a parallelogram. And I have vectors u and v defining two adjacent edges of a parallelogram. They have a common initial point or vertices of a parallelogram. Suppose the angle between them, this angle is theta. Now, if I draw a perpendicular down here, so I have this right triangle. They don't tell me what is the simplest formula for the area of a parallelogram. Yes, base times height, because you can think of a parallelogram as a union of two triangles. So you have 1/2 base times height for each, so together it's just base times height. Okay. So, so u here is the base. So the base is the magnitude of u. Now for the height, we can use right triangle trigonometry to determine that the height, this height of this right triangle is equal to the length of a hypotenuse, which is magnitude of v, times the sine of the angle between u and v. So the height is magnitude of v sine theta, and that just comes from sine theta being opposite over hypotenuse. So the area comes from a product of these. So magnitude of u, magnitude of v, sine theta, but that's the magnitude of their cross product. So that's another formula for the area of a parallelogram. That if you have vectors in however many dimensions that define two adjacent edges, then you take their cross product, find its magnitude, and that's the area. So now if I have a triangle where I have u and v, vectors sharing a common initial point, that's one of the vertices of a triangle. Finding two of the three edges. So the area of a triangle would be 1/2 base times height. So that'll be 1/2 magnitude of cross product of u and v. So as an example, suppose I have a triangle. Certainly not drawn to scale, where the this vertex is point P1. It's 1, 1, 0. So the triangle sitting in three-dimensional space. And then I have second point P2, which is 3, 0, 4. And then the third point P3, which is 0, 5, and 2. Okay. So I want the area of this triangle. So what I can do is I let U be a vector from P1 to P2. So when I'm subtracting components of these vectors. Okay. Okay, something seems to be wrong with my notes. Dang it. Yes, there's something wrong with my notes. Okay. Alright, so what would the components of the vector from P1 to P2 be? Yeah, 2 minus 1, 4. Yeah, I have 3 in there in my notes for some reason. Okay. Now define V to be a vector from P1 to P3. Okay. All right, so now we have a vector, so we have, this is V. And this is U. So now we would need to compute the cross product of U and V. So that's this 3x3 determinant. Okay. So we have -2, -16. Then we have -4, -4, so it's -8. Then we have 8 minus 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 makes a minus. 8 minus 2 is. Wait, yes, is or sorry, 8 minus 1. 7. So then we need to compute the magnitude of that. W square root of 18 squared plus 8 squared plus 7 squared. So 324, 364, 388 plus 49 is 537.
Wait, hold on. Uh-oh.
Um, 88, yeah, 437. Okay. So then the area is 1/2 that. Yes. Just about how that one went. So given 3 vertices of a triangle, find vectors between 2 pairs of vertices. Take a cross product of them, magnitude of a cross product. And then divide by 2, and that's the area of a triangle. And if it's a parallelogram instead of a triangle, but you just don't, same process, you just don't divide by 2. For parallelogram, make sure it's, if you're getting all 4 vertices, make sure you choose 2 adjacent edges. Yes,
For the J. I'm getting 4 times -1. I'm sorry, 2.
oh,
2 times 2 is 4.
oh, wait, that should be,
Yeah,
hold on.
I'm getting, all right, so I'm getting -4, -4 minus 4.
-8.
But does that not flip?
Oh,
The
okay. When doing the determinant, you come to minus J.
Yeah,
Okay, then you do the determinant of this. Which would be +8.
yes.
But then because of the J part being negated, then the actual component therefore is
Oh,
-8.
okay.
I know. Question? Okay. All right, one more geometric application. For volume. On a parallelepiped. Be difficult to draw, but. Okay, so. Here's your parallelepiped, and at a certain vertex, if you let. U, V, and W refer to the three edges of a parallelepiped that emanate from that one vertex. So the key here is that they share the vertex as a common initial point. Okay. Then. All right. Now, the area of this shaded region right here, that is a parallelogram defined by vectors U and V. So the area of that parallelogram is cross product of U and V. Okay. Now, but then we need the height of the parallelepiped that would take W into account. Okay. So. Vector Z in my notes, I haven't even said what it is. Problem. Okay. Well, yeah, Z. Okay, and based on what I have in my notes, so that's the cross product vector. That is the vector that is orthogonal to both U and V. So that'll be a vector going in this direction. That's perpendicular to the entire parallelogram that is the base. Okay. Okay. Now, if I look at the angle between this cross product Z and the remaining edge W, this angle here, theta, the angle between them, then by right triangle trigonometry, the height of the parallelepiped is equal to the hypotenuse, which is magnitude of W, times the cosine of the angle between them, cosine theta. So that means that the volume which would be the area of the base times the height, would be equal to cross product of U and V times magnitude of W times a cosine of the angle between the cross product and W. So another way of writing that is if I take the absolute value of the cross product of U and V dot product with W. And this is what I mentioned this earlier, that is it's the absolute value of a triple product. So that gives you the volume of a parallelepiped. So if you have UV and W sharing a vertex as an initial point, you pick two of those, doesn't matter which two, take their cross product. Then take the dot product of that vector that comes from a cross product with the remaining vector, so W in this case. And then don't forget to take the absolute value because the dot product is allowed to be positive or negative. Like if I took U and V and switched them, I'd have a change of sign in the whole expression. That's why I take the absolute value. Now, a convenient way to express this as a determinant is if you just put all three vectors in a matrix. That is equivalent to expressing the cross product of two of them as a determinant, like we've been doing, and then taking a dot product with your remaining vector. So now, but again, don't forget to take the absolute value of that. If I switch two rows of that matrix, that flips the sign of the determinant.
Can't really have a negative volume like that.
Yeah, so that's the absolute value. Okay. What are the things we can do with cross product? So more general formulas than we've done before for area of a triangle, volume of a parallelepiped. So questions about any of these formulas? I do have time for an example of the last one.
See,
Okay. Let's suppose that our basically drawn parallelepiped. Vectors U free W that come from that vertex as the initial point. Let's suppose that U is the vector 3, 1, 1. E is the vector 1, 5, 1. W is the vector 0, 1, 1, 2. So to get the volume, first compute the cross products. Again, you choose any two vectors. I just choose U and V. So that's going to be 1 times 1 minus 5 times 1. And then 1 times 1 minus 3 times 1. Then I have 3 times 5 minus 1 times 1. So that gives us minus 4, minus 2, and 14. All right, and then you take the dot product of that with W. So U cross V vector vector -4, -2, 14, dot. Vector 0, 1, 2. So we get -4 times 0, -2 times 1, plus 14 times 2. Turns out to be 26. And you take the absolute value of that, but that's still 26. So we conclude that the volume is 26. Whatever units you like. That's it. Anything you miss or possibly? I'm just making sure my notes are correct. Apparently, you never know. I just remind myself that these were written back when I was a stressed out, untenured professor. Okay. All right, coming out of the end. Well, that's the end of the notes anyway. But the next 3 class periods talking about lines and planes. Good times ahead. Yeah. Oh.